From the fuel in some cars to the sanitizer on our hands, alcohols are literally everywhere. They're some of the most versatile organic compounds out there. So what exactly makes something an alcohol? How do we make them? And what's the secret to their reactivity? Well, over the next few minutes, we're going to break down all the chemistry behind this fascinating family of molecules. Let's dive right in.
So here's the game plan. We'll start with the absolute basics. Then we'll compare the two big ways ethanol is made. After that, we'll look at its most important reactions, see where it pops up in daily life, and we'll wrap up with the key facts you absolutely have to remember.
All right, first things first. What actually makes an alcohol an alcohol? Well, it all boils down to its very specific chemical structure. Okay, so alcohols are part of what we call a homologous series. Now, that sounds fancy, but it just means they're all in the same family, and they have similar chemical personalities. And that entire personality comes from one tiny feature, the hydroxyl group, which we write as OH. This little bit of oxygen and hydrogen is basically the command center for the whole molecule. It dictates pretty much everything about how it behaves.
And every single member of this family follows a general formula: CnH2n+1OH. If you look at it closely, you might notice it looks a whole lot like the formula for an alkane. The only difference is that one hydrogen atom has been kicked out and replaced with that all-important hydroxyl group. And trust me, that one simple swap changes everything.
Now let's talk about how we draw these things, because this is super important. On the screen, you can see methanol, that's the one with 1 carbon, and ethanol with 2. Now, for anyone studying this, listen up. A displayed formula means you have to show every single bond. See that little line connecting the oxygen and the hydrogen? You can't forget that OH bond line. It's such a classic way to lose easy marks on an exam.
Okay, so we know what they are, but how do we actually make ethanol? Probably the most famous alcohol of them all. Well, on an industrial scale, there are two main ways to do it, and comparing them tells this really cool story of trade-offs, a real battle between nature and technology. First up, we've got fermentation. This is the old-school, biological method humans have been using for thousands of years. You've got enzymes and yeast that take glucose, sugar basically, and convert it into ethanol and carbon dioxide. The conditions here are pretty gentle. You need a yeast catalyst, a nice warm temperature between 25 and 35 degrees Celsius, and, this is critical, it has to be anaerobic. That means absolutely no oxygen. Why? Because if oxygen gets in, the whole thing goes wrong and you end up making ethanoic acid, which is just vinegar.
And method number 2 is the total opposite, the hydration of ethene. This is a pure, heavy-duty industrial process. You just react ethene with steam. The equation is super simple, right? C2H4 plus H2O gives you C2H5OH. But the conditions, whoa, they are anything but gentle. You need a scorching 300 degrees Celsius, a crushing pressure of 60 to 70 atmospheres, and a solid phosphoric V acid catalyst to get the job done.
And this table just lays out the trade-offs perfectly. Fermentation, it uses renewable stuff like sugarcane, which is great, but it's a really slow batch process. And the ethanol it makes is impure, so you have to distill it. Hydration, on the other hand, is a super fast, continuous process that gives you really pure ethanol. The catch? It relies on ethene that comes from crude oil, a non-renewable resource, and it takes a ton of energy to maintain that crazy high temperature and pressure.
So, we've got our ethanol made by either gentle biology or industrial brute force. What makes it so useful? Well, that all comes down to its key chemical reactions, especially when you burn it or oxidize it. First, combustion. Let's be clear. Alcohols make excellent fuels. Ethanol burns completely, and it does so with a really clean, pale blue flame. As you can see from the equation, it just produces carbon dioxide and water. No soot, no mess. It's also a highly exothermic reaction, which just means it releases a whole lot of energy. That's exactly why we use it in spirit burners and as a biofuel.
But what if you don't want to just burn it? Well, you can oxidize it in a more controlled way to form ethanoic acid. In the lab, a classic way to do this with a strong oxidizing agent like acidified potassium manganate 7. And this reaction gives you an amazing visual cue. The solution starts out as a vibrant deep purple, and as the reaction happens, it turns completely colorless. It's like a chemical magic trick, and that distinct color change is your proof that oxidation has happened.
So these chemical properties aren't just for textbooks and labs. They translate directly into all the different ways we use ethanol out in the real world. Ethanol is an absolutely fantastic solvent. It can dissolve a lot of things that water just can't handle, like oils and resins.
That's what makes it so perfect for things like perfumes, glues, and varnishes. We've already talked about how it's a clean-burning, high-energy fuel, right? That's why it's often blended with petrol. And of course, it's the key ingredient in alcoholic drinks like beer and wine, a use that goes all the way back to that ancient fermentation process.
All right, let's lock all this in. Time for a rapid-fire review of the absolute key takeaways. These are the non-negotiable facts you've got to have down cold.
Ready? Let's go. The general formula? CnH2n+1OH. The catalyst for hydration? Phosphoric V acid. The golden rule for drawing it? You always draw the OH bond line. And the conditions? Remember your units. 25 to 35 degrees Celsius for fermentation and a whopping 60 to 70 atmospheres for hydration. Got it? Good.